Alright, so DeMoivre's theorem is used for raising complex numbers to a different power. And this includes finding the roots of complex numbers. And so we do this by using the polar form of these complex numbers. So let's say we have z and we want to raise it to the nth power. This is represented in polar form as r times cosine theta plus I sine theta, right? And we're raising all of this to the nth power. So what this becomes is r to the n times cosine n times theta plus I sine n times theta. So this is what we get when you raise that number to the nth power. So let me show you an example. I remember the number we used in the last video for some of our examples was, let's say we have our complex number w and it's equal to square root 3 minus I. So this, right, is just 2 times square root 3 over 2 minus 1/2 I, right? And we could also use the formula r equals the square root of a squared plus b squared to find the radius, which is r, and then theta equals, the tangent, inverse tangent of b over a, inverse tangent of b over a, like I mentioned in the previous video, where, our complex number is a plus bi. That's our complex number. But we already went over the few ways you can do this, and I'm just going to use this way because I like it better. But if you want to know more, just check out the last video. So this becomes, because we know cosine is square root 3 over 2 and sine is negative 1/2 when the angle is 11 pi over 6. So this becomes 2 times cosine 11 pi over 6 plus I sine 11 pi over 6. Okay, so that is our complex number and in polar form. And now let's say we want to raise this to the 6th power. So w to the 6th power would be 2 to the 6th times cosine of 11 pi over 6 times 6, oops, I covered up the cosine a little bit, plus I sine 11 pi over 6 times 6. All right, so this becomes 2 to the 6th, which is 64, cosine of 11 pi over 6 times 6. So this is cosine of 11 pi plus I sine of, again, 11 pi. And so that on the unit circle is right here, right? Because any odd number of pi's is going to be here, and an even number is here. So this means cosine is negative 1 and sine is 0. So this becomes 64 times negative 1 plus 0i. And so this is just 64 times negative 1. And so w to the 6th, or rather square root 3 minus 1 all to the 6th, is going to be equal to negative 64. All right, now let's talk about taking the roots of certain numbers using DeMoivre's theorem. So since we already have this number and we know one of the 6th roots of it, let's just try to take the 6th root of negative 64. So we say that the formula for this is z to the 1 over n. So, or we can say z to the whatever nth root is equal to r, the nth root of r, times cosine of theta plus 2 pi k over n plus I sine theta plus 2 pi k over n. And so k is just going to be so k is going to be, if we have 6 roots, it's going to be 0, 1, 2, 3, 4, 5, 6. Oh, sorry, 0 to 5. That's what k is going to be for finding the n roots. So let's say we have negative 64 and we have to take the sixth root of it. So first, let's try to find a way to represent negative 64 in polar form. So if there's no imaginary parts, there's no I, that means on the unit circle, it's either going to have to be here or here. And so I'm just going to say that it's over here, because that way we can say that, let's call this complex number z. It's going to be equal to 64 times cosine of pi plus I sine pi, right? Because this means it's 64 times negative 1 plus 0 I. Okay, and now we want to take z, and we want to take the sixth root of it. So that means we have to take the sixth root of 64, and then cosine of pi plus 2 pi k over 6 plus I sine pi plus 2 pi k over 6. Okay, so this means that our roots are going to be, well, the square root of 64 is going to be 2. Oh, yeah, it's just going to be 2. We could use negative 2, but we'll get to that as you'll see here. And then cosine of pi plus 2 pi k over 6. What the heck does that mean? So basically what this means is I'm going to be simplifying, first off, I'm going to be simplifying cosine theta plus I sine theta to just cis from now on because it's easier. But what this means is that our first root is going to be at cis of when k is 0, okay? So that's just going to be pi over 6 plus I sine, oh, actually, I just said I was simplifying this to cis. So it's just going to be cis pi over 6. And then our next root is going to be 2 times cis, because remember 2 is just the sixth root of 64. Cis times k when k is 1. So that'll be 3 pi over 6, so pi over 2. And then our next root would be 2 times cis, and then we have pi plus, when k is 2, we have 5 pi over 6, so 5 pi over 6. And as you can see, pi over 6, 3 pi over 6, 5 pi over 6, we just keep going on and on. So this is cis 7 pi over 6, and then we have 2 times cis 9 pi over 6, or 3 pi over 2, all right. And then our sixth and final root is going to be, actually let me erase this, it's not consistent, is going to be 2 times cis 11 pi over 6, which if you'll notice, that is the number that we raised to the sixth power to get a negative 64, right? So this we can confirm is one of the roots. But if we went on one more, that would be 2 times cis 13 pi over 6, which is just cis pi over 6. So that's why we don't have to go past the number of roots we have, right? We have 0 to 5. So we have 0 to 5, and that's 6 numbers, 6 roots. So once we go past that, we're just repeating ourselves. And these should be all of the roots. And we can write this out in complex form, like a plus bi as well. So that will probably be a little complicated, but we can. It's actually not complicated at all. It'll just take a little time. But first, let me show you this on a graph. Who could have guessed? Me showing it on a graph. So this is going to be pretend it's our unit circle, okay? And so just pretend there's an imaginary unit circle. I'm going to estimate the angles. So 2 is our radius for all of these angles, and 1 is cis pi over 6. So let's just say about here, okay? The other one is cis pi over 2. Actually, let's do this in a different color so it stands out. Here, and then cis pi over 2, which is here. Oops. And then we have cis 5 pi over 6, which is here. And so then we have cis 7 pi over 6, which is going to be about here. And then 3 pi over 2, which is here. And so 11 pi over 6, which is here. So obviously all of these are going to be 2 pi over 6 spaced out, right? Because that's what we're adding here, 2 pi over 6 each time. But I feel like it's really nice to look at this graphically because now, well, if you have a number, like this is 64, and it starts, wait, where does it start? It starts at cosine pi plus I sine pi, well, you know that if you're trying to find the 6 roots of it, well, you're first going to just start with pi over 6, and then every time you're going to add 2 pi over 6, 2 pi over 6, 2 pi over 6, 2 pi over 6, 2 pi over 6. And so, this is just, I feel like, a really nice visual to kind of represent in your mind what these complex roots are actually, looking like. Another reason why this is important to be able to visualize is because sometimes they'll ask you to make like polygons in the complex plane using the roots of something. So if you don't know, like, wow, these roots are going to make, there's 6 of them, they're going to make a hexagon, and you don't know how far apart they are. Because like now we know, oh, the radius is 2, it's a hexagon, so all of these sides are going to be 2, we can calculate the area. So now you know that because you know this is what the graph looks like. And I've seen questions like that. So I feel like that's another reason why it's important to just think about this. But other than that, I mean, I guess I'll convert 1 to complex form like a plus bi in rectangular form, just so you can see it. But I'm not going to do all of these roots because I feel like that's a little redundant. Let's just pick a random one. Let's pick this one. So we have 2 cis 5 pi over 6. Let's do it over here. And that's just 2 times cosine of 5 pi over 6 plus I sine 5 pi over 6. This becomes 2 times, what's the cosine of 5 pi over 6? It's negative square root 3 over 2 plus I sine 5 pi over 6, so that's plus 1/2 I. And so this becomes negative square root 3 plus 1. And I am sure that if you raise this, you did DeMoivre's, and you raise this to the 6th power, this would also become negative 64, which you can see through this because, raising 2 to the 6th is 64, and multiplying both of these by 6 will give you a cosine of just 5 pi, which is negative 1. So, as you can see, all of these roots will do the same thing because the pi appears odd. Anyways, that's DeMoivre's. Hopefully this did help a little bit. And yeah.